Hi, this is Professor Tiffany Martin with Medical Microbiology, and we are in Chapter 5. We just finished aerobic cellular respiration, so make sure you know that well. And we want to go on to do anaerobic respiration and fermentation to finish this up. So, anaerobic respiration goes through the exact same process as aerobic respiration. It just doesn't use oxygen. Now, anaerobic respiration is rare. You back to this. Anaerobic respiration is rare. It only happens in a few weird bacteria. The bacteria who live at the bottom of the sulfur springs where there's no oxygen, or in volcanic vents, or deep in the ocean. For those bacteria don't have access to oxygen. Those bacteria still want to do respiration and get that 38 ATP, very efficient oxidation, but they just don't use oxygen as the final electron acceptor. That's the only difference. Now, do not confuse this. I get students that get confused because when we talk about things you've learned in nutrition and biology, whatever, we talk about being able to make ATP anaerobically as humans. And that's true, but it's not respiration. It doesn't involve the electron transport chain. It doesn't involve all of that things. So yes, we have some pathways where we can make ATP anaerobically without oxygen. That's a good thing, those plan Bs, those backup plans, but it is not respiration. Okay, it uses something different. Respiration, let's go back to the PowerPoint now. Respiration is when you use an inorganic molecule as the final electron acceptor. So anaerobic respiration, rare, few bacteria, and it uses an inorganic molecule as the final electron acceptor. So sulfate is inorganic, nitrate is inorganic, oxygen is inorganic. So aerobic, did I say that right? Cellular respiration is called respiration because it uses an inorganic molecule as the final electron acceptor. What makes it anaerobic is that it's not oxygen. It uses sulfate or nitrate as the final electron acceptor. All respiration uses an inorganic molecule. Aerobic respiration uses oxygen. Anaerobic respiration uses sulfate or nitrate. Okay. All right, so that was the second part there. The final electron acceptor is an inorganic molecule. Now, there is another way that we can make ATP, and this is called fermentation pathways. There's a lot of different fermentation pathways. I'm getting ahead of myself. Before we do that, so it is respiration. It involves an electron transport chain. Anaerobic respiration involves an electron transport chain. It produces the same amount of ATP, or about the same amount, compared to aerobic respiration. So this is what you need to know for anaerobic respiration. Rare bacteria uses sulfate or nitrate as the final electron acceptor, so it is anaerobic. It is respiration because it uses an inorganic molecule like sulfate or nitrate. Aerobic respiration is also respiration because it uses an inorganic molecule. It also uses an electron transport chain, so it also makes about 38 ATP. Okay, so now let's talk about some other pathways that are not respiration, that don't use an inorganic molecule as a final electron acceptor. There is pathways called fermentation, which use organic molecules as a final electron acceptor. And that's the definition of a fermentation pathway. It uses an organic molecule as the final electron acceptor. All right, so fermentation pathways, there's a lot of different ones. Depends on which enzymes you have, as depending on which pathways you can do. Yeast are capable of fermentation. We talked about fermentation with the wine and making alcohols as an end product. So that's a fermentation pathway. But those bacteria that Pasteur found, they were also undergoing fermentation. The difference was their end products were acids, which is why it didn't turn into wine, but it turned bitter and acidic. We actually have fermentation pathways in our own cells, and our muscle cells are capable of a lactic acid fermentation pathway. All right, so let me tell you a story. We're in quarantine, and I'm back walking again. But if anybody has tried to go running, if you haven't been running in a while, maybe you ran in high school and you decide, okay, I'm going to do it again. It's been a long time. So you're like, okay, today's the day. And you get out there and you start running. And you're like, okay, I got this. And you're running and you're running. And suddenly, maybe 10 minutes in, you start breathing hard. And you're like, oh crap, didn't used to do this, but you're breathing hard. You can't get enough oxygen to your muscle cells. You are asking your muscle cells to do something they haven't done in a while. They're not, they've lost kind of that ability to get enough oxygen to the cells for the work that you're asking them to do, making you run. Because of that, you're not getting enough oxygen to your muscle cells. Remember, we need that oxygen. It's the final electron acceptor to make ATP. You are using more ATP than you have available. You don't have enough oxygen to keep that going. Now, it's not cyanide. Luckily, you're still breathing. Like you think you're going to die, but you're not. You're still breathing. You're still taking in air. So some of your muscle cells are getting enough oxygen to keep ATP being produced and keep you running, but not all of them. So your body is responding and it's telling you, stop, you're gonna die. So you can either do a couple of things. You can stop and walk. That would be what I would be doing. You can stop and let your oxygen, catch back up and get more of that oxygen into you. If you're a trained athlete, your body is trained. You carry oxygen very efficiently, and so you're not going to wear out as fast as someone who's starting back up. But you can stop and walk for a little bit and let that catch up. Or you're like, gonna push on through. So you keep going and you keep going and you keep going, and you're pushing your body more to do more than you have the oxygen to keep that ATP going, keep that electron transport chain going. So what happens in your body? In your cells, glycolysis, you ate that breakfast that morning, you got glycolysis going, you're breaking it down, it's making pyruvic acid, it's sending it to the Krebs cycle. You've got a lot of NADHs coming to the electron transport chain to drop off their hydrogens, but you don't have enough oxygen, right? You're breathing heavy, you don't have enough oxygen. Those electrons have backed up in your electron transport chain. Those NADHs come, but there's nowhere for them to go. They can't drop off their electrons. So they're hanging out. You don't have enough oxygen. What's going to happen to those NADHs? Well, you don't want to die. Your body doesn't want to die. You have some plan B pathways to keep making ATP and to keep you from dying. Remember those pyruvic acids? They were your end products from glycolysis. Again, you have nutrients, you've got pyruvic acids. So pyruvic acid is there. You have lots of NADHs that came from the Krebs cycle and that, but they can drop off their electrons. So here they are. They will actually, instead of going to the electron transport chain and just backing up and forming a line, they will actually give their electrons to pyruvic acid. So NADH will become NAD+. Ooh, oxidized or reduced. Oxidation involves loss. NADH got oxidized and now made NAD pluses. Pyruvic acids got reduced. They accepted a hydrogen. They now become a new molecule, which you should know these names. It's short. You can memorize these. C3H4O3 picked up some hydrogens and became C3H6O3. So now we've made a new molecule, and this molecule is lactic acid. Your body has the enzyme needed to catalyze this reaction. So your body starts, your muscle cells start making this lactic acid. Why do they do this? Well, this NAD plus can go back to glycolysis and pick up some hydrogens from glycolysis. And if you remember, in glycolysis, we make some ATP in glycolysis. Do you remember how many? You made 4, but you had to use 2, so you net 2 ATP. Now, 2 is not 38, but 2 will keep you alive. Your body has a backup plan, and it'll make this lactic acid so that you can keep at least that going. So some cells are doing respiration. You're still breathing, but not all cells will. You get a lot of backup, and then you get this lactic acid. You heard of lactic acid before? A lot of times after a workout, you get that muscle soreness, and this is after an aerobic workout. You get that muscle soreness. That lactic acid is not as easy to get rid of as carbon dioxide and water. That's easy to get rid of. So that lactic acid builds up in our body, causes some soreness from those acids. It takes a little bit more time for you to get used to it. Now, my fitness people, what do your trainers tell you when you do that? They tell you to keep moving. That will keep that lactic acid moving through. So that's what they're telling you to do. So this is what's happening. This is in your muscle cells. This is considered a fermentation pathway. Why? Because fermentation uses an organic molecule as the final electron acceptor. So here's my organic molecule, and it picks up the hydrogens to form lactic acid. Now, if you notice, remember how we subtracted all the carbons from glucose? Pyruvic acid has 3 carbons, and we still have 3 carbons. It didn't get completely oxidized. We left a lot of energy on the table, and now our body just has to get rid of lactic acid. It can't use it anymore. So this is why it's better to undergo cellular respiration, and these are short-term plan B, we don't want to die kind of pathways. So muscle cells are capable of lactic acid fermentation. Other cells, some bacteria, can make lactic acids in fermentation. You remember those, the bacteria that was undergoing fermentation and turning the grape juice acidic. It was producing these lactic acids from there. Okay, let's look at another fermentation pathway. And again, there's many. We're just highlighting 2. And this is the alcohol fermentation pathway. So we can take those pyruvic acids from glycolysis. And, well, we can't. We do not have the enzyme. But yeast have an enzyme that can take pyruvic acid and convert it into acetaldehyde. They undergo decarboxylation, and pyruvic acid then becomes acetaldehyde. Then acetaldehyde accepts those electrons from NADH, and the end product is ethyl alcohol. So this is how yeast, which has this one enzyme, gets to make alcohol as an end product, and us, which do not have this enzyme, ends up making lactic acid. Now, it would be interesting if instead of working out, if we had this one enzyme, if we produced it, instead of working out and being sore after a workout, we could work out and make a whole bunch of alcohol and be drunk out of a workout. That may make a whole difference in motivation to exercise, but we don't and we can't. And so yeast can do this, we cannot. Okay, so back to our chart. Hadn't seen this in a while. We have glycolysis is the first step, and we've been going down cellular respiration. But you can see pyruvic acid, that end product, is also the first step in these fermentation. Glycolysis is the first step in this fermentation pathways. It takes pyruvic acid, depending on which organism and what enzyme it produces. It may either take it down a lactic acid or an acetaldehyde to ethanol, or there's other fermentation pathways we're not talking about, or not utilizing. Okay, so why is this cool? Fermentation is a big deal. We know it's a big deal because we can make wine. So fermentation pathways, we have utilized the microorganisms and their abilities to undergo fermentation to benefit our lives. So your wine is easy, beer, bread, all of that uses Saccharomyces, a yeast that undergoes fermentation pathways that produces ethanol as its end product, or ethyl alcohol. There are other ones. Clostridium bacteria undergo fermentation. They have different enzymes. They end up producing end products that produce acetone and isopropanol. This is our like our rubbing alcohols, nail polish remover. Acetone is what's in nail polish remover. So different bacteria can produce this, and then we can use it. Products that we can use. There are some bacteria. Lactobacillus is one that produces lactic acid. This bacteria is responsible for yogurt. Your yogurt and your live yogurt cultures, when they talk about live bacteria, these are the bacteria lactobacillus that is used to take milk, your sugar, and create and undergo fermentation and produce acidic end products that turn it into yogurt. Cheddar cheese, same way. Different bacteria are involved in taking milk, and then they will turn it into cheddar cheese. There are different bacteria that produces a different acidic end product that causes Swiss cheese. If you notice, Swiss cheese has holes, right? Cheddar cheese doesn't. This particular bacteria, propionic acid, has a different flavor. Your cheeses have a different flavor. It also produces a byproduct of carbon dioxide. So while this is going on and it's undergoing fermentation and producing the carbon dioxide, that's why Swiss cheese has holes, these pockets of carbon dioxide gas that end up there. Okay, fill it out. See how it goes. How'd you do? For both of the above fermentation pathway, pyruvic acids are the precursors, acetaldehydes are intermediates, byproducts, and then when 2 NADHs are oxidized, acetaldehyde accepts the hydrogen. Did you do the next page too? In lactic acid fermentation, NADHs are oxidized. The pyruvic acids themselves accept the hydrogen, but in alcohol, In alcohol fermentation, ethyl alcohols are the end products, lactic acid fermentation, lactic acids are the end products. So know the end products from these. General features: before fermentation occurs, you have to have glycolysis. And if you notice, no ATP is produced during fermentation. The reason our body does it is to regenerate NAD+, which can go back to glycolysis and keep us from dying. Fermentation, oh, that's what this says. Fermentation serves to regenerate NAD+. A final electron acceptor is an organic molecule. That's what makes it fermentation. Fermentation occurs in the cytoplasm. Whether or not you can do it depends on the enzyme. Again, one enzyme, and we could be producing alcohols after a workout. Doesn't work that way. Fermentation does not involve an electron transport chain, and it doesn't make the same amount of ATP. That is it. Chapter 5, it's a monster. Stay with it, and good luck, and we'll answer questions on Thursday. And your exam is Monday. Talk to you later. Thanks.